In this lesson, we are going to write an explicit rule for a sequence, as well as write a recursive rule for a sequence. An explicit rule gives an as a function of the term's position number n in the sequence. Explicit rules is what we have been dealing with in 11.1, 2, and 3 so far. The arithmetic explicit rule, where it was an equals d times n plus c, and the geometric explicit rule, which was an equals a1 times r to the n minus 1. What is new to us is the recursive rule, which gives the beginning term or terms and then a recursive equation that tells us how an is related to the preceding terms. So it may give us a1 and a2, and for the following terms it will give us a way to use a1 and a2 to find 3, 4, 5, and so on. The following two examples are our first examples of the recursive rules. Notice that we are given a1 and a rule for the following term. So we know it says write the first 5 terms of the sequence. So we know that a1 equals 1. So a1 equals 1. So a2 is going to be equal to a2 minus 1, because we are on the second term, so our n equals 2 squared plus 1. a2 minus 1 is actually a1, and we know that a1 is 1. So we have that is equal to 1 squared plus 1, which is equal to 2. a3 is going to be equal to a3 minus 1 is a2 squared plus 1, which will be equal to 2 squared plus 1, which will be equal to 5. Now a4 is going to be a3 squared plus 1, which is going to be 5 squared plus 1, which is going to be equal to 26. And last but not least, a5 is going to be equal to a4 squared plus 1, so that will be equal to 26 squared plus 1, which is going to be 677. So those are the first 5 terms of the sequence. We have a1, a2, a3, a4, and a5. So in the next example then, grab a different color here. We know that a1 is 2, a2 is also 2, and then every term after that will be an minus 2 minus an minus 1. So if it wants us to find the first 5 terms, we know that a1 is 2, and we know that a2 is 2. So a3 then will be an minus 1, so a3 minus 1 minus an minus 2, so 3 minus 2 minus a3 minus 1, which will be a1 minus a2, which is going to be 2 minus 2, which is 0. So if we follow that pattern, then we need to find a4, which is going to be a2 minus a3, This is a little hard to read, I apologize. Which equals A2 was 2 and A3 was 0. So we will get 2 for A4. And then A5, we will get A3 minus A4, which will be 0 minus 2, which is negative 2. So once you get the hang of it, you notice that there's just a pattern that we follow, and we will get each term that we are looking for eventually. A4 was 2 and A5 is negative 2. So the next thing we're going to do is just try a couple of examples of more recursive rules, get the hang of these things. So we have that A0 is 1, A1 is AN equals N times AN minus 1. So if we have A1, 1, and then AN minus 1 is A0, which was also 1, so we get 1. A2 will be N times A1, which was 1, so we get 2. A3 is 3 times A2, which was 2, so that's 6. And 4, we get 4 times 6, because that was A3, which is 24. And 5 times 24 is 120. Now notice that these are actually the factorial numbers, or the product of all integers from 1 to n. So if you remember factorials, 0 factorial is 1, 1 factorial is also 1, 2 factorial is 2 times 1, which is 2. 3 factorial, just going down, 3 times 2 times 1, which was 6. 4 factorial, 5 times 3 times 2 times 1, which was 24. And 5 factorial, 5, 4, 3, 2, and 1, which is 120. Just kind of cool. So we will try one more of these. We see that A1 is equal to 1, A2 is also equal to 1. A3, now we have AN minus 2, which is 3 minus 2, which is A1, plus AN minus 1, which is 3 minus 1, which is A2. So we get 1 plus 1, which is 2. So if we follow down the sequence, we get A4, 4 minus 2 is A2, 4 minus 1 is A3, which will be 1 plus 2, which is 3. And then we get A4 plus A5, A3 plus A4, skipped a step there. A3 plus A4, which will be 2 plus 3, which is 5. So again, we're noticing that we're just following a pattern. First it was 1 plus 1, then it was 1 plus 2, then it was 2 plus 3. Now it's going to be 3 plus 5, which is 8. Using the last two terms, 5 plus 8 is 13. Using the last two terms again, which is 8 plus 13, which is 21. And these are actually the numbers in the Fibonacci sequence. Just another cool rule that we are using. The next thing that we are going to work on is we're going to use the same bits of information and we're going to write both types of rules. So if we know that A1 is 15, sorry about that. We know that A1 is 15 and we know that D is 5. We can start writing the terms. We have to remember that D is for the arithmetic sequence, which it gives us right here, but sometimes it won't. So we have to remember that D is for the arithmetic sequence. So if we know that D is 5, we know that we're adding 5 each time in between the terms. So our term list will be 15, 20, 25, 30, and so on. So, writing an explicit rule is what we did in section 11.2 in the arithmetic sequence section. So, if we remember, our explicit rule for the arithmetics is an equals dn plus a constant, cx, whatever you like to use. Then we just fill in our information. So if our an is a1 equals 15, our d we know is 5, finding the first term 1 plus our constant, we get that our constant is equal to 10. So our rule, our explicit rule, is an equals 5n plus 10. From there, we would just be able to pick any term, a10, a30, anything, and plug it into the formula to find the value of that term. So for the recursive rule, separate, different color. This is when we have to determine what we do to the next term and use the term prior. So this time we have still a1 equals 15, and an is actually just going to be equal to an minus 1 plus 5. Why does that work? Well, an minus 1 for the second term would be 15 because it would be a1, add 5 to that, 20. So we just use the very term before that, add 5 to every single term, just like we figured out for the explicit rule. So this would be your recursive rule because it depends on the term prior, and this one is, again, your explicit rule because it does not depend on the rule prior. It just says plug in a value and I'll tell you what the term is. So in this section, we are going to be doing the geometric sequence, and if you remember correctly, for the explicit rule, our geometric sequence rule was an equals a1, which is the first term, times r to the n minus 1 power. So it gives us a1, and it gives us r, which remember is the ratio. So we have to remember in this lesson that if we're given d, remember it's arithmetic. If we're given r, it's the geometric. So all we have to do for the explicit rule is just plug these numbers in. So we get that an equals a1, which is 4, times r, which is 0.2, to the n minus 1. So there's our explicit rule, just like we have been doing this whole time in 11.3, the geometric sequence section. For the recursive rule, we are going to use the r, which is the ratio, and we are also going to use the term prior. So our recursive rule, a1 is equal to 4, and an is equal to 0.2 times the term before it, which is an minus 1. Now, why does this make sense? When you were trying to find the ratio in the geometric sequence, what did you do? You looked at the first term, the second term, or the second term, the third term. You said, what are they doing in between each term to get to the next? You're multiplying, right? So if a1 is 4, then a2 would be 0.8, a3, so on. So what did you do to the first term to get to the second? You took it times 0.2. So that's why this recursive rule makes sense, because it says you take 0.2 times the term just before it to get your term. Now this last example gets a little bit trickier for us. They give us the sequence and they want us to now find a recursive rule. So we have to determine which terms we're using to find the next term or the next term. So we're going to look at the sequence pretty carefully. If we took 1 plus 1, or 1 plus 0 would give us first term to second term, which is 1. Second term to third term would be 1 plus 4, or 3, to give us 4. So we know that we're not using the arithmetic sequence because 0 doesn't equal 3. So let's cross that off. If we use the R version, which is the geometric, we would take 1 times 1 to get us 1 for the second term. And from the second to the third term, we would take 1 times 4 to get us 4. Well, 1 doesn't equal 4, so that's not going to work out. So the next thing that we can do is remember in the recursive rules that you can use more than one of the terms previous to get to the next one. So what if we use the first two terms? Well, 1 plus 1 is 2, and how do you get to 4 from there? Well, you take it times 2. Okay, how about the next ones? We have 1 plus 4 is 5. Well, how do you get to the next one? Take it times 2. So it looks like we have a pattern, and that's really good. So if we need to write our terms, remember that they always gave us the first or second depending on how many terms in the recursive rule they were using. So we have to list A1, which is 1, and A2, which is 1, because we're going to be using the first two terms for our rule. So then AN is going to equal 2 times AN minus 1 plus AN minus 2. Because if you remember, we used 4, or we used the first two terms, 1 and 2, to get to 4. So we used AN minus 1, which was 1, AN minus 2, which was 1, times 2 to get us 4. And we did the same thing for term 4. Just to show you that this is working, A4 would be 2 times, and minus 1 is A2, or A3, and then n minus 2 was A2, so that is 2 times 1 plus 4, which is 2 times 5, which is 10, which is A4. So we know that our rule is working. So the most important thing that you need to take from this lesson is the terminology of the explicit rule versus the recursive rule. Remember that the explicit rule is what we have been using up to this point in 11.2 and 11.3, and even in 11.4 we used the explicit rule when we were finding the infinite sums, right? So the recursive rule is new for us, and that just means that we're using the beginning term or terms to determine the next terms. So it is very important still that you remember the equations that we've been using and remember how to write these rules, because they will be useful in writing your recursive rules and determining the patterns. And that will conclude this lesson.